We'll be looking at the question 16, October 2020 paper. The first question starts off with, this question is about magnesium, bromine, and magnesium bromide. The weighted mean mass compared with 1/12 the mass of carbon-12. So that's the definition. It is asking, explain what is meant by the term weighted mean mass. You see, when you're doing relative atomic mass calculations, what you're doing is you are getting the mass of the isotope, and you are multiplying it by its percentage abundance, and you are then adding them all up together, and you're then dividing it by the total percentage adds up to 100. Now, so in terms of what is meant by the term weighted mean mass, the average mass of isotopes is not acceptable, is not enough, sorry. And there's this idea that, you know, you can either put this formula into words, or you can say taking into account the relative abundances of the mass of the isotopes. So you could say sum of the isotopic mass multiplied by the percentage abundance. Sum of meaning adding them all together. And then dividing by the total abundance. This is the weighted mean mass. Yep, this is, I prefer this. This is the allow guidance, but the main answer was quote, taking into account the relative abundances of the isotopes. Moving on, this is a dot and cross diagram for magnesium bromide. Outer electron shells only. You see magnesium is in group 2. It loses those 2 electrons, and it has a 2+ charge. Always write down the number first and then the charge. And you see bromine is in group 7. So 1, 2, 3, 4, 5. Whenever we're filling up electrons, it's good to do like this, like passengers on the bus. And then double up. 1, 2, 3, 4, 5, 6, 7, and like so. And because each bromine has gained an electron, let's put these come from the magnesium. Straightforward 2 marks. Calculate the number of total ions. Total number of ions in this much mass of magnesium bromide. The first step we do is work out the moles of magnesium bromide, and magnesium is 24.3 and we have 2 of them. This gives you the moles of magnesium bromide. You see there are 3 moles of ions per compound. You got Mg2+, Br-, Br-, Mg2+, Br-, Br-. So this answer we multiply by 3. This gives you the total moles of ions, and we then multiply it by Avogadro's number, and that gives you the answer. We want it to three significant figures I've got here. 1.71 times 10 to the 22 number of ions. And the mark scheme supports that. Multiply it by 3 and then multiply it by Avogadro's number and the answer to 3 sig figs. This is looking at this question. It's an essay question. It's asking about, you've got explain the physical properties using your knowledge of structure and bonding. You see, whenever we're looking at structure and bonding, we need to think about the type of bonding between the atoms or molecules or ions, and even consider if there's any force of attraction between molecules in the form of intermolecular forces. So let's do one at a time, and then we can do some comparison. So magnesium, you see with magnesium, you have metallic bonding. So you've got metallic bonding. Does it want? Has metallic bonding. The structure is giant metallic lattice. And you see magnesium has delocalized electrons. The term lattice is like a regular arrangement of the particles, in this case, positive metal ions. Now, for bromine, the structure is simple because you've only got individual Br2 molecules. It's simple molecular. Simple molecular, and what type of intermolecular forces do you have between them? We have London forces. And those London forces are from the Ildid forces. And what are Ildid forces? Dipole induced dipole forces. Simple molecular has London forces between molecules. Be specific. So you've got your Br2, and it's that weak intermolecular force between them. And the third one, you've got magnesium bromide. You see magnesium bromide, it has a giant ionic lattice structure. What's holding the particles together is the ionic bonding. What is ionic bonding? The electrostatic attraction between oppositely charged ions. Actually, while we're here, you see metallic bonding. What is metallic bonding? Metallic bonding is electrostatic electrostatic attraction between positive metal ions and delocalized electrons. Hope you can read the writing. Ionic bonding, electrostatic attraction between, so you need to mention, you got ions here, you got molecules here, and you got your positive metal ion and your delocalized electrons here. Now, this about the bond strengths, you see, this idea that metallic bonding, metallic and ionic bonding requires a lot of energy to break. Let me just get the wording right here. Metallic and ionic bonds requires a lot of energy to break. That's why they tend to have a very high melting point. Whereas London forces requires very little in comparison. Okay, now in terms of conductivity, why does magnesium conduct electricity? Magnesium conducts electricity both in solid and in liquid form. Bromine, doesn't matter if it's a solid or a liquid, it does not conduct electricity. Magnesium bromide conducts electricity when it's a liquid molten state, but not when it's, it conducts electricity when it's in a molten liquid state, but not in a solid state. Why is that? We've seen these questions again and again from year one, this idea that magnesium has delocalized electrons. And what is it about these delocalized electrons? They are mobile or can move. So whether it's a liquid or a solid, you see with magnesium bromide in solid state, what are the ions? In solid state, the ions are fixed in position and cannot move. Magnesium bromide, yeah, cannot move. And in molten liquid state or even aqueous, how do you spell aqueous? My spelling's gone. How do you spell aqueous? AQU, wait a minute. AQU. Oh, it's an E. My goodness, what's happening to my spelling? AQUEOUS, aqueous. Now, and in molten liquid state or aqueous, the ions are free to move. Bromine, which is Br2, does not conduct electricity. Why is that? Because it has no charge carriers. You see the Br2 molecules, there's no full charges. They may have partial charges, but there's no full charges on them, which explains why it does not conduct electricity. These are all the main points, and you try to be as detailed as possible, and you'll gain all the marks from there. Moving on to the next part of the question. What you've got here, the enthalpy change of hydration of bromide ions can be determined using the enthalpy changes below. Now, this is an interesting question. These are not very common. What they've done in this question, they've combined a Born-Haber cycle to do with atomization, to do with formation, atomization, electron affinity, and they've combined it with the enthalpy change of solution cycle. So this is like two cycles combined into one. And so it's easy to get a little bit perturbed, but we are going to stick to our rules that we've learned with Hess's law, that the overall enthalpy change, irrespective of what route is taken. So asking here on the dotted lines, add the species that are missing. You see, you've got the first ionization energy. This must be the second, Mg2+, gaseous plus 2Br, gaseous plus 2 electrons. That explains these 2 electrons are then gained to give you Br-. That's that level. And if you look here, so MgBr2 is formed here. It must be formed from its elements in their standard state. And from here to there is the atomization of bromine. Bromine at those over here. Using your completed energy cycle, calculate the enthalpy change of hydration of bromide ions. You see, of bromide ions, we are trying to work out hydration of bromide ions. This is what we're trying to work out. And we're trying to get from here to here, but we don't know what that is. So what we're going to do, we're going to use Hess's law and go the other direction. You're going against this arrow, against this arrow, against, with, and with. Just repeat that, against, and with this arrow, and with this arrow as well. So all of those will be minus, but the last 2 will be positive. So let's get these values going. I'll just write on the cycle so you can see. What you've got here is the hydration of magnesium. where's the hydration of magnesium? Is minus 1926, but it's going to be minus 1926. Then you've got the electron affinity of bromine, and you see there's two bromines, so we times that by 2, and you're going against it, minus 325 times 2. Again, you're going, that's the second ionization energy. It's going to be minus 1450. And then you've got the first ionization energy, minus 736. And then you've got, what's that? Atomization of magnesium, which will be minus 148. So going against the arrow. And then you've got atomization of bromine, minus 112. And then it's going to be plus the enthalpy change of formation of magnesium bromide. Be careful about your signs. 3 atomization of, what's that? Sorry, formation of magnesium bromide, minus 525. Atomization of bromine is supposed to be, wait a minute, electron affinity. And where is atomization? Yeah, atomization of 112 is supposed to be multiplied by 2. We would have made a mistake there. And the last one is enthalpy change of solution. Can't see. Oh, solution's right at the bottom. So you're going with the arrow, so we plus minus 186. And we now just calculate this. So minus 1926. (325) times 2. Remember, be careful of the signs. Minus 1450 minus 736 minus 148 minus 112 times 2. Use brackets. And then plus minus 525 plus minus 186. I've got here an answer of 693, a negative value. And you see, if you look over here, this change is for 2 bromide ions. What's the enthalpy change of hydration? The enthalpy change of hydration is where 1 mole of ions have dissolved in a solution to give you aqueous. Get the exact wording for you. Enthalpy change that takes place when 1 mole of isolated gaseous ions is dissolved in water, forming 1 mole of aqueous ions under standard conditions. So this idea that 1 mole of aqueous ions are formed from gaseous ions dissolved in water. And this answer we got here is for 2 moles. We divide that by 2. Minus 346.5. Yep, that's correct as well. Write the equation for the lattice enthalpy of magnesium bromide and calculate the lattice enthalpy of magnesium bromide. So what we got here is, you see, lattice enthalpy is where 1 mole of an ionic compound, ionic solid, is formed from its gaseous ions. Just curious, was there no lattice enthalpy here? No, there wasn't. Because lattice enthalpy is going from the gaseous ions to the solid. And they didn't show that step, and that's what they want us to work out. So by doing that, we're going to bypass? We're not going to use the hydration enthalpy. We're not going to use dishydration enthalpy, and we're not going to use the solution. Okay, so what that means, we've done this before as well. The enthalpy change of lattice enthalpy is equal to the enthalpy change of formation minus everything else. So what we'll do, let's just cross out these, we don't need these. And we've done our electron affinity for bromine. And we need the atomization of bromine also to be multiplied by 2. And it's going to be enthalpy change of formation. So it'll be that value minus everything else. Let's do that on our calculator. Plus minus 525 minus 325 times 2, 48 minus minus 736. So by doing that, the answer we get is minus 2433. So look at the mark scheme, minus 2433. And the equation is the gaseous ions. Yep, and that is correct, ladies and gentlemen. That ends this question. We'll see you tomorrow.